Namaskar, Adab, Sat Sri Akal. How are you, students? I hope that all of you are doing very good in your studies. So, if I am talking about the chapter that we are ongoing is moving charges and its effects, magnetic effects. I have told you in the first lecture of this chapter that how due to the moving charges, magnetic field is also observed around it. Correct. We have seen different cases. We have studied about Oersted law, okay, Biot-Savart's law, these kind of things that we have studied, and these things have explained that whenever there is a charge that is moving through a conductor, that means some current will be coming, and if there is some current is coming, obviously there is some magnetic field is also around that loop that is present there. Correct. Now in this lecture we are going to study more in depth about a kind of topic. The topic name is Ampere's circuital law. Ampere's circuital law. It is a lot similar to, if I will say, in electrostatics. A lot of things are relatable from magnetism to electrostatics. For example, this Ampere's circuital law. If I will tell you from how it is related, you remember you have studied Gauss law. What was Gauss law in electrostatics? Tell me. What? Correct. Gauss law was what? Integration of E dot ds is equals to q in divided by epsilon naught. Here the same relation will become, q will become E dot ds, electric field will become magnetic field. See, what is the statement of this Ampere's circuital law? The line integral of B dot dl along any closed path in a region is equals to mu naught times the total current crossing the enclosed area. Same as the statement of Gauss law. There, what we have focused on, what is the net charge that is present inside the Gaussian surface. Here we are going to focus just in a similar way. What is the net current flowing through a Amperean loop? For example, let's suppose here are two current that are shown. One is going in upward direction, one is coming in downward direction. What you will do? Firstly, make an Amperian loop. What this imaginary surface is? This imaginary surface is called as Amperian loop. This imaginary surface is called as what? Amperian loop. And then how I am going to write? I will take an element on this Amperian loop of dl, and then I am going to integrate all this dl vector, and then I am going to write this equation, that surface integral of, there what was kind of integral in electrostatics? Area integral. Here it is what? Line integral. Line integral of B dot dl is equal to mu naught into, what is the net charge flowing inside? Net current that is flowing inside, you will be writing that. And if I ask you, tell me how you will be writing net current, you can write here, one is going in upward direction, one is coming in downward direction. That means you can write either I1 minus or I2. This way you will be writing this. Correct. Now there are lots of bytes of applications that can be understood from here. Like we have derived from conventional method for state wire, infinite wire. We have, if you remember, that we have derived in a complete element way. Then we have calculated the angle complete. We have seen those kind of things. Now here what I am going to tell you, here we will be deriving everything again by using Ampere's circuital law, and it will become very easy. But from board's point of view, if you are asking me, I will suggest that go with the conventional method, because you know, the more you will be writing in the copy, the more marks you will be getting. So conventional method you have to prefer in board. Otherwise, in competitive exam or for understanding purpose, Ampere's circuital law is good. If you understand Ampere's circuital law, that means you can easily derive anything. I will tell you how. It is very easy. Don't worry. Now see. I've told you, if the directions of current are different, you will be taking one as positive, one as negative. That is very obvious thing. And already I've told you, this is an Ampere's loop that you will be drawing, and then you will be integrating that Ampere's loop. If I'm talking about the steps, what will be the steps that you have to follow? Firstly, you will be drawing an Amperian loop. You have to just blindly follow these steps. Every single time you will be getting the answer. I will tell you how. Then use a right hand thumb rule. I will tell you how to find the directions, because directions is integral part of this chapter. Consider a dl vector and then integrate the dl vector, line integral of the dl vector, and finally you will be having the answer. Check the angle between the dl vector and the current, and then you can quote your answer. Okay. Now see what you will be doing for a closed loop, closed line integral of B dot dl. For, let's suppose you are having an infinite wire. You are having an infinite wire like this. Okay. You are having an infinite wire like this, and some current I is flowing through it. And you want to calculate at some point P, you want to calculate what will be the magnetic field at some point P. This is what you want to calculate. How you will be calculating? See. Firstly, what is the first step? Draw an Amperian loop. Draw an Amperian loop. This is your Amperian loop. Okay. Now what we will be doing? Take an element, dl element, and now write the equation. What you will be writing the integration? Line integral b dot dl is equals to mu naught into net current passing through this Amperian loop. Can I say net current? What is the net current passing through the current loop, students? I, only simple I. Now what I will be writing? Integration of dl vector is equals to mu naught into what is the net current? Small I will represent because small I is there. Now what is the integration of this dl? I can say what? Tell me if I integration is what? Simply summation, correct now? So I will simply add all these small element for this complete loop. Tell me what the summation will be coming. Can is the circumference of the circle, correct now? So what I will be writing here, b into 2 pi, what is the radius that is given? 2 pi d, that is the circumference of the circle, is equals to mu naught into I. Now b is equals to mu naught into I divided by 2 pi d. B is equals to mu naught I divided by 2 pi d. This will be the result, and of course this should be the result because we have derived already and we have got the result, same result that we have got by the conventional method, by taking an element, mentioning the angles, that for an infinite wire the net result that you will be getting is mu naught I divided by 2 pi d. So we have cross checked it also that our results was coming correct. Is it clear? Simple. Let's see some more applications. Okay, mu naught I divided by 2 pi d. Now this is the next thing. Current is flowing on the surface. There is a cylindrical kind of wire now this time given. The thickness is a little bit more, and but the current is flowing only on the surface of the conductor. Is it clear that what is the meaning of the current is only flowing on the surface? Let's suppose if this is a cross sectional area, if I have to explain, let's suppose this is a kind of cylinder. Okay, this bottle is a kind of cylindrical wire, and but the condition that is given here is the current that is flowing is only through the surface, not from the middle portion. Only current is passing from here the edges. Okay, this is the condition that is given, and now you have to calculate what will be the magnetic field at two kind of point at you have to calculate. One is for inside portion and second one is for outside portion. So let's see one by one. Let's firstly calculate for inside portion. Current is passing from this edges. If because this is a 2D diagram, I should reflect like this. I think that it is looking like only current is passing from the edges. Okay. Now, if I have to calculate at an inside point, what is the first step you are going to do? What is the first step you will be doing? Go at an inside point at any random point at point P. Make an Amperian loop. Step 1. Make an Amperian loop. Step 1 and take a dl vector and write the equation. B into line integral of dl is equals to mu naught into net current that is coming inside. Now tell me students, if you are taking a point inside, what is the net current passing? Can you imagine? What will be the net current? Can I say isn't it zero? Because all the current that are flowing are from the surface, not from the inside portion. Not a single current is flowing from the inside portion. All the current is flowing only from the surface. That means net current inside portion will be zero. If this current is equals to zero, what I can say about the magnetic field? Magnetic field is also going to be equals to zero. Clear? Is it clear that it is also going to be equals to zero simply? But what will be happening if I am calculating for the outside portion? Let's do that also. At some any point D, at some distance D at point P, I want to calculate magnetic field. What is the first step? I will be taking an Amperian loop. Firstly, I will be taking an Amperian loop. Then what I will be doing? I will be writing the equation that B into surface integral of dl. I will take an element dl and I will integrate this line integral is equals to mu naught into net current that is coming inside. Mu naught into I, the net current that is coming inside. Now tell me, what will be the integration of this dl vector? The radius is d. That means what will be the integration? 2 pi d is equals to mu naught into I. Mu naught into I, because I can say what is the net current that is coming inside. Can I say total current that is flowing? Represented as I, capital I. You can represent it as capital I, no problem. So can I say all the current are coming inside from for this bigger Amperian loop? Simple. So now the result will be how much? It is the same result for the infinite wire, mu naught I divided by 2 pi d. Simple as that. This will be the result for the outside portion. That means what you can say, what kind of variation you are getting from D? Here you can see for inside portion, magnetic field is equals to 0. That means there is no relation, and here B is inversely proportional to D. If the question will be asking you about any relation, you can simply draw the relation or the curve also. Correct? Like here, what is this curve that is drawn? I have told you for inside portion, this completely is what? This completely is your inside portion, and this completely is your outside portion. This completely is your outside portion. For inside portion, what you will be saying about the magnetic field? Magnetic field is equals to 0. And for outside portion, magnetic field is inversely proportional to R. Inversely proportional to R, and inversely proportional to R, what kind of curve you can say? It is nothing but equal. It is rectangular hyperbola. Rectangular hyperbola curve is there, so you can simply draw it. I have told you a lot of times about rectangular hyperbola. From thermodynamics, we are studying about rectangular hyperbola. If still you are having any doubt in rectangular hyperbola, you can ask to your maths teacher. Okay. Now the next one is a little bit more interesting about. Why I am saying that it is a little bit interesting, the reason I will tell you now. Now see, magnetic field due to long cylindrical wire case is same, but this time what is the change that is happening here? Notice that current is flowing uniformly through the conductor. Now last time what I have told you, that current is only flowing from the surface, only flowing from the outer surface. But this time current is uniformly passing through the center points also, from inside point also, from the surface also. Okay? So this time there will be some inside current also, and that calculation will be very interesting. I will tell you how to calculate. Once you got to know that what is the net current design, that's all things are very simple. Because every time what we are doing, every time we are taking an Amperian loop, we are taking a DL vector, and we are integrating. And what is the integration of DL vector? Till now it is very clear. Summation of all this DL vector is going to give you the circumference of the circle. Correct? That means that value is going to be equal to 2 pi d. Clear? So let's see. Let's do it for this one. Firstly, for the inside portion. Inside portion, what is the first step? Always we take an element of Amperian loop. We will draw at some point P, and I want to check what will be the net current flowing inside. Okay, net current flowing inside. Fine. Tell me what kind of surface distribution this is. Can you say it is what kind of distribution? Current distribution. Surface. We are talking about the surface. How much surface? So tell me, this I current is flowing through how much area? Can you say, is it true to say that pi r square through pi r square area, how much current is flowing? I. What is the total area? This cross sectional area, pi r square radius is given as r. So through this pi r square, what is the net current flowing? I. Is it true to say? If I'll ask you from 1 unit area, how much current will be passing? I divided by pi r square. Any problem? From 1 unit section, if this much of the current is passing, so if I'll ask you, tell me from pi d square area how much current will be passing. So isn't it true to say from pi d square area, the net current that is flowing is pi r square into pi d square? Yes or no? Are it is same or not from the chocolate thing? Again and again I have told you that, let's suppose if there are 10 students in your class, correct? 10 students in your class. I am giving you 20 chocolates. I am giving you 20 chocolates. That is, one student will have how many chocolates? Very simple, 2 chocolates. That is, if I will ask you 3 students, I will have how many chocolates? 6 chocolates. 5 students, 10 chocolates. 6 students, 12 chocolates. How you have did it? See, now try to relate it. 10 students, how many chocolates? 20 chocolates. 1 student, how many chocolates? 2 chocolates. 3 students, how many chocolates? 6 chocolates. How you have did it? You multiplied it by 3, na? Are you able to relate? Are na? Correct na? So now how you will be writing? Our equation is again same way. B dot surface integral, line integral B dot dl is equals to mu naught into net current flowing inside. Now how you can write net current? Pi will get cancelled, and the net current is I d square divided by r square. Correct? Now what is the line integral you will be writing? Line integral you will be writing 2 pi d. Already I have told you about this. Mu naught into I d square divided by r square. This d and this d will simply get cancelled, and d can be written as mu naught I d divided by 2 pi into r square. Mu naught I d divided by 2 pi r square. That is the result we will be getting. Correct? and it is also defined as current density, because in current electricity we have studied a lot about current density. That there was the first time when this term was introduced. So we have defined basically a current density. Now it's up to you how you are going to proceed. Is it clear? So if I'll ask you the variation, let's understand the variation also. How magnetic field is varying with this distance d, I can say simply it is directly proportional. Correct? Is it true to say that it is nothing but it is directly proportional? Any doubt? Clear? Oh, very good. Now come to the outside point. Outside point, I will say it is same. Why it will be same? Let's discuss that also. Outside point, let's suppose at some point P you want to find magnetic field, draw an Amperian loop, and take a dl vector and try to integrate this dl vector and write the rest of the things. What is the equation that you write? Not till now you should tell me what is the equation. B integration, line integration of dl vector is equals to mu naught into net current that is flowing inside is I. B into what is the integration of this dl vector? Integration is going to give you 2 pi d is equals to mu naught into I. That means magnetic field at point P will be equals to mu naught I divided by 2 pi d. Can you say this is the same result? It is the same result for so outside point is not changing at all. Outside point, again, if I am talking about the relation, I can say B is inversely proportional to D. What kind of curve we are going to get? Rectangular hyperbola. Clear? Correct. So here is the variation. I have told you for inside part it is directly proportional to D. For outside part again it is inversely proportional to D. And when it is inversely proportional to D, it is called as rectangular hyperbola. I hope that this will be clear to you. Now there is a basic question. Let's try to solve this question quickly. See what you can say. The question is given. Firstly read the question properly. Then let's analyze this question. The magnetic field at a distance r from a long wire, that means it is a long infinite wire, and magnetic field at a distance r at point A carrying current I is 0.4 Tesla. Is 0.4 Tesla. That means at this point the magnetic field is given is 0.4 Tesla. The magnetic field at a distance 2r will be. What will be the magnetic field at this point? What will be the magnetic field at this point? Firstly, tell me how will be writing the formula. What is the formula due to a infinite wire? The magnetic field formula is mu naught I divided by 2 pi r. Mu naught I divided by 2 pi r. So let's write it. Mu naught I divided by 2 pi r is equals to how much? 0.4 Tesla. And here if I have to write magnetic field, how I will be writing? I will be writing mu naught I divided by 2 pi. What is the radius that I am telling you? It is nothing but 2r. That means can I say it all these things are same but only divided by a factor of 2 is coming. That means 0.4 Tesla is the net magnetic field of that value divided by 2. I can simply say the answer will be 0.2 Tesla. I hope that most of you are be getting the answer. So correct answer is option A. Clear? Easy question. Option A is the correct answer. I hope that this will be clear. Now the next two very important instruments that you have to study is one is solenoid, okay, and second one is toroid. These two are very important and it have very high probability to ask in the board exam. Very high probability it has having, and the results that you will be getting from here is very important for competitive exams. So for all the perspective, these two things, toroid is anyways little bit less important from solenoid, but solenoid is very important. Okay, so try to understand, because the derivation we are going to see the derivation in both ways. First I will tell you by the conventional method also, and then I am going to tell you with the Ampere-Circuital's law also, because Ampere-Circuital's law make the derivation very easy. But from the conventional method, if you are targeting some good competitive exams, it is very important. And even in the boards, I will suggest that remember the conventional method more effective. It will be more effective for you. Firstly, let's understand what is solenoid. Solenoid is an electromagnet. It is an electromagnet. That means it show a behavior of a magnet. Why it shows? Actually, what will happening when you will be watching the solenoid? This is a long conductor, okay, and it is wounded by a wire. It is wounded by a wire, okay, and always some current is flowing through it. And I told you in the first lecture only, when some current is flowing through anything, it will induce some magnetic field as well. So that's why now, depending on the direction of this current, some magnetic field will also be introduced into this solenoid. and that's why it behaves like an electromagnet. And the purpose of which is to generate a controlled magnetic field through a coil wounded to a tightly packed helix. This shape is called as helix, and that's why it is having a magnetic field as well. This is the complete concept of solenoid. Let's see what will be the results that we will be getting, important result, and how we will be reaching to that results. That is more important. Here it is very simply shown. This is the higher potential, this is the lower potential. That means current is coming from here and going through here. Due to that, the direction of the magnetic field is south to north. I will telling you how you'll be calculating the direction. Anyways, for circular things, I told you always just curl your hand in the direction of the circular where the current is going. Automatically, your thumb is going to give you the direction. Very simple thing. And if you are changing the polarities, here you can see from the first case and change the polarities. Due to that, what happened? The direction of magnetic field is also changed, and we have already understood this thing in the first lecture only. This is very obvious for solenoid also. Same thing is represented in the terms of directions here. Okay, you can do, and you can check the directions. Here it is going like this. So just curl your, here it is going like this. Curl your hand in the direction of magnetic field, you will be getting the direction, and you can see what is the direction in the left direction. And here you can see here it is the direction of current. Here it is going like this. If you imagine it in properly in 3D, you have to curl the hand in like this, and you will be having magnetic field from south to north direction. Correct? Fine. Now let's begin how to get to the result of a solenoid, how to calculate the magnetic field due to a solenoid. That is the important thing. Okay. Before that, I have told you in the last lecture how to find the magnetic field due to a circular loop at some point P, at some distance D. Okay. So if I am talking about that result was equal to B is equal to mu naught I R square divided by 2R square x square power 3 by 2. And what is that R? R is the radius of this circular loop, and x is the distance from point P from the axis. On the axis, what is the distance for point P is x. So I hope that this formula is clear to you, because we are going to derive from this formula only. Okay. Now see, very properly try to watch what I did. Firstly I will do what? This is the solenoid now. Now what are this cross and dot are representing? What is the, let's understand that also. Imagine it in complete 3D. What is happening? This kind of circular winding is there. Circular winding, circular winding, circular winding. Now if current is flowing, what I can say, when the current is going like this, it is, we are watching from this side. Okay, please try to understand it in 3D. You are going inside. That means at this point, what I can say, the current is going, it is looking like from this perspective, it is going inside, and the current now it is coming outside from here. That's why it is represented as dot. This is the only meaning of this thing. Okay. So from some any random point P, I will be taking an element and cutting a cross section of the solenoid of thickness dx. This is what I am going to do, and I will write the effect of that cross section, the magnetic field I will be writing. How I will be writing? I will be writing small magnetic field. Okay, small magnet, and the length is also given. Length is given as a. Okay. I will be writing mu naught. What was the formula due to a circular loop? Mu naught I into r square. Mu naught I into r square, that is a radius square, divided by r square plus x square power of 3 by 2, and then there is a factor of 2. Correct now? But tell me, what will be the current that will be flowing through this cutted cross section? I have told you, if there are n number of loops, you will be multiplying with n, okay, and only with the current. But here, how many number of loops will be cut down? Tell me, what is number of loops? N is defined as number of turns divided by per unit length. Correct? So if I have to write number of turns, it will be equals to n into, what is the length? Here, what is the length we have taken, students? N into dx. So I will be multiplying this term as like this. I will be writing mu naught I will be multiplied with n dx r square divided by 2r square plus x square power of 3 by 2. And now you will be integrating it from the length, because now you have a variable dx with respect to x. Let's suppose this point is some a, and this is x. We will be taking this as x is equal to 0, and this point, the end point, let's suppose x is equal to minus of b. For a moment I have taken. So what is the limits of integration I am going to apply? I am going to integrate it from minus b to some a. Now I don't know how many of you have studied integration till now. This is what the integration you have to perform. Correct? Now there are two different ways your maths teacher will be suggesting maybe some way, but in physics mostly we prefer it to convert into angles. I will tell you how I am going to convert it, but let's write the better form of that also. See what I am going to do. This is a little bit cluttered, so try to understand, or let's do it. Limits of integration, just remember it is here it is mentioned as minus a and that is plus b. Let's see on the blank page. I am going to draw the same thing. Diagrams will be a little bit cluttered, so please focus. It is very important. This is a solenoid. Okay. This kind of circular winding is there. This kind of circular winding is there. Correct? Let's draw the. This is the radius. This is the radius. The length given for this solenoid is L, and let's assume here is a point P that we have. And this point is given as x is equals to b. This point will be of course a reference line, that means x is equal to 0, and let's assume this is x is equals to minus of a. And let's write the dv also, that what we have to integrate. Integration is for mu naught I, if I am wrong please correct me, mu naught I into dx into r square divided by 2 r square plus x square power of 3 by 2. Correct? What we have did, we have cut it out. And two more things I am naming here. If I am naming this as angle theta 2, theta 1, I have to integrate it from theta 1, and I will be naming this angle as theta 2 from this point 2. Now this is the given things. Now I am going to take an element. Again I am explaining you. Anyways, we have taken the element already. At some general angle theta, I am going to cut a cross section. I am going to cut a cross section of thickness dx. I am going to cut a cross section of thickness dx. This is the cross section that I have. And how many number of turns of this cross section? I have already told you it is equals to n dx, and that's why there is a factor of n dx also I have multiplied here. Correct now? Now I want to convert this in terms of angles for a better integration. So, and what are the limits of integration? Limits of integration is from minus a to b. Okay, minus a to b. Or you can say from b to minus a also. B to minus a, because we are in terms of angle, we are starting from theta 1 and coming till theta 2. So if I am converting this in terms of angles, I will be integrating the same thing here, right? Theta 1 at what is b? Here it is b, here it is minus a. I am starting this from here. What I can say about the angle 0. Here what is angle theta 1, and I exactly from this point I want to start integrating. I want to integrate from theta 1. I will integrate till theta 2, because at minus a what is the angle theta 2. This angle I have shown you theta 2. Clear? Now what I am going to do the integration. Understand here. Tell me what you can define in this triangle. This distance is r. This base is given as x. This base is given as x at a distance x. If I will ask you to define cot of theta, how will you writing what is cot of theta? Base upon perpendicular, and tan of theta perpendicular upon base. Base upon perpendicular, that is it is equals to x divided by r. So what you can write for x students? It is equals to r cot of theta. And now if I will ask you to, because I am going to use a substitution, if I will ask you to tell me dx differentiation, what will be saying? Minus of r is the constant multiplied, and what is the differentiation of cot theta? Cot theta differentiation is nothing but cosec minus of cosec square theta d theta. Exactly, this is what we are going to have as a result. Now try to take the constants out of this integration and try to write this complete result. When you are taking this out of integration, what is that? You will be writing mu naught I into r square divided by, and rest of the things you can take 2 also common, and then there is a factor of minus also, so take the minus also outside. Now at the place of dx, what you are going to write? You are going to write r cosec square theta d theta, and divided by, here what you are going to say, what is the at the place of x, what you are going to write? R square cot square theta. That means you are going to take r square common from here. Take r square common. Inside what will be left? Inside it will be left as 1 plus cot square theta. 1 plus cot square theta is nothing but equal to cosec square theta. and the whole power is power of 3 by 2. Correct? When you will be taking this as outside, so net, can you say this will be whole square and whole square, this power will be cancelled, that means here it will become r cube. The net term that will be in denominator will be, if I am writing the next step, I will be writing r cosec square theta d theta divided by, in denominator it will become r cube cosec cube theta. Now this cosec cube theta and cos square theta will be cancelled out. Here this r and this r square will become here cancelled, and this r square and this r square will be here cancelled. Now what is the integration only left, student? Now it is a very simple, good, cute integration. Sin theta d theta from angle theta 1 to theta 2. What is the integration of sin theta? It is equal to minus of cos of theta integration theta 1 to theta 2. Take that minus out of this, and can I say this minus and this minus is going to be cancel out. So finally this was the outside point, and finally inside what you will be getting, cos of theta 2 minus of cos of theta 1. Is it clear? This was the complete depth result that I don't think so that I have tried my best to explain you in complete depth for this complete derivation. It is very important, students. Again I am saying, don't go for the shortcut that is Ampere circuital law, because Ampere circuital law will never give you this result, cos of theta 2 minus cos of theta 1. It only calculates for an ideal solenoid. It doesn't calculate for any general solenoid of length L. I will tell you what is the result for ideal solenoid also. From this result only we are going to derive that also as well. Okay. So the final result that you have to remember, see this much of long integration when you will be doing, you will be having mu naught ni, because r square term will completely cancel, mu naught ni divided by 2 cos of theta 1 minus of cos of theta 2. Correct? From theta 1 to theta 2 you have integrated. I think I have put it the limits a little bit wrong. It will be theta 1 to it is missed. You will be integrating from cos of theta 1 to cos of theta 2. So finally the result that you will be remembering here is mu naught ni divided by cos of theta 1 minus of cos of theta 2. This is what you have to remember. Is it clear? Is it clear? So now some special cases will be there that we have to understand. Remember this result, we will be moving forward there, and we will be calculating for ideal solenoid from this general result only. This is the standard thing that you have to remember. So let's suppose now you have to calculate magnetic field at the end of a solenoid. That means this is the length only. Now this is the end point P, and here you want to calculate the what will be the magnetic field at the end of the solenoid. Now tell me what will be the angle theta 1. What will be the angle theta 1? Can you say if it is a long solenoid, if I am saying it is a very long solenoid, can you say theta 1 will be tending to what? 0 degree, and theta 2 will be tending to, and it will be exactly 90 degree. Correct? If I am talking about long cylinder, that means this, the more I am going to increase the length, the less this angle will be equal. I hope that this will be very clear to you in imagination. You can see what is the angle subtended by us to the stars. Very small angle is there. If I am talking the angle that will be subtended between two stars, why that angle? Because they are very far distance. But still the angle is very small because the distance is very long. Correct? This is the same thing. So just satisfy those things here. Cos of theta 1 will be equal to 0. Cos of theta 2 will be equal to 90. Cos 0 is equals to 1. Cos of 90 0. 1 minus 0. The result that you will be getting at the end of a solenoid, will be equals to mu naught ni divided by 2. This is also an important result. But what will happen at the center of the solenoid? See, now we are going to see what is ideal solenoid. Ideal solenoid can be called because it have to satisfy two conditions. First condition is it should be very long. That means this length L should be very long in compared to this R. This is the first condition. And the second condition, it is the number of turns that are having here should be very large. These are the two conditions for an ideal solenoid. And now if I am writing for an ideal solenoid, at the center point, if I will be calculating magnetic field due to ideal solenoid infinitely long, tell me what will be the theta. This angle is this distance is very long. That means can I say theta 1 will be tending to 0 degree, and what I can say about theta 2? Theta 2 is also tending to 0 degree. This angle, because this side also it is very large. That means this angle, theta 2 is going to be tending to 180 degree. Because from here you are calculating, that means theta 2 will be increasing. If this distance is increasing, this angle will be increasing, and it will be tending to what? 180 degree. Now satisfy these two things. Cos of theta 1 minus cos of theta 2. Cos of 0 minus cos of 180. What is cos of 180? Cos of 180 is nothing but minus of 1. Minus of 1. Here it will be cancelling the factor of 2. That means at the in the midpoint, in the middle area of a long solenoid, the result is mu naught n I simply. And this is the standard result that you will be getting from the Ampere circuital law as well. Ampere circuital law will also going to give you the same result, mu naught n I. I will tell you how that will also be coming. That is a very simple one. If till here it is clear, you have completely understand the concept of solenoid, you can solve any kind of question. If you are very much clear in your mind how you have came till here, that means you can crack any question of this topic, solenoid. I hope that this have helped you. So this is the curve that I will tell you. What kind of curve I will explain a little bit. In the middle portion, always you will be tending nearly to in the middle portion you will be having mu naught ni, and when you are reaching at the end points, the magnetic field will be directly, all of a sudden it will have a down spike, and you will be having magnetic field mu naught ni divided by 2 factor, mu naught ni divided by 2 factor on the both of the sides. Correct. And what about the direction? What about the direction? I have already told you. Just curl your hand in the direction of the solenoid, and you will be having the direction as well. So now magnetic field due to solenoid using an Ampere's law. Ampere's law, it is very easy. I will tell you how. See what you will be doing. Here it is a solenoid. Here it is the diagram of solenoid, and take an Amperian loop. I have taken a spherical Amperian loop. I have taken an Amperian loop. Very good. Now what I am going to do? I am going to write the equation. This is not the same. Integration. This is the simplest. Integration. How I will be going to do the integration? I will be integrating for the 4 sections. Firstly, I am going to integrate from AB section. I will take a DL and I will writing B dot DL for this AB section. Then I am going to write for this DL section. Sorry, AD section, and then DC section, D to C section, and then C to B section, and net I will be writing mu naught into I. Mu naught into I, that is what I am going to write that as net current that is coming inside. Let's suppose this distance is x, so number of turns, you know, it is n is equal to number of turns per unit, length small n, and that means if I have to write n, I will be writing n into length, that is I have taken as x. Correct. So we have written all these complete equation. So for one section. Now tell me what will be the value of for this A section. B dot DL. B dot DL. Tell me, in this AB section, is any current is also flowing? Is any current is also flowing? Tell me. I can say no. There is no current flowing into this section. That's why I will say B dot DL will be simply here. It will be equals to 0. Now come to the next one. AD portion. I will say what is the direction of magnetic field? If this is coming like this, tell me, this is the current that is going inside and it is coming out from here. That means what is the direction of magnetic field I am getting? This is the direction for magnetic field. This is the DL vector or the current that I am assuming. Okay. This is the DL vector and this is the direction for magnetic field. Tell me B dot DL. What is the angle between them? 90. If the angle between the B and the DL and there is a dot product, that means cos of angle will be writing 90. That means due to this also the effect that you are going to write is 0. So can I say for BC section also it will be equals to 0. Now what is left only? Only portion that is left is CD portion. Now we will be writing due to the CD portion. You can see here it is 0, here it is also 0, it is outside the solenoid, so the magnetic field also equals to 0, and here you can say again 0. Only portion that will be left is CD portion. And how I am going to write the equation for CD portion? Simply write the equation for CD portion, integration of D magnetic field dot DL. What is the length that you have written? X is equals to mu naught Ni into x. This x will be simply get cancelled because after integration, of course, this DL vector integration, it is going to give you x. So B is equal to simply mu naught into Ni. Exactly the result that I have told you, the final result that we have derived from this complete conventional method. This is what finally also you are going to get as mu naught Ni. Is it clear? Is it clear, all students? So Ampere circuital law was very easy, but the actual fun that you will be having is the real conventional method. If you are going, that will give you the real kick. If some students are aspiring for the tough challenging things like for JEE Advanced someone is targeting, So I would say that go with the second method, that will give you the real fun. Okay. Fine. Now the second thing that we are going to discuss is toroid. Toroid is very easy. We are going to simply integrate from Ampere-Circular's law. Toroid, what is the result? That is not important. Firstly, understand what kind of shape it is called as toroid. Toroid is also kind of solenoid, but the only difference here is there was straight, long, cylindrical, or the long conductor was there. But here you will be having a circular. Circular, that means there is toroid is essentially a solenoid. I told you that is bent in the shape of ring. It is only in the shape of ring, and the current will be coming from here. That means if current is coming, some magnetic field will also be introduced. If magnetic field is introduced, that means it will have some current is introduced, that means some magnetic field is also introduced into the toroid. And the thing that we have to understand is how much magnetic field will be there. That's it. That is what we have to calculate. So let's calculate. This is a very simple and interesting case. Let's suppose you want to calculate at the inside the toroid portion. This portion, what you will be doing? Draw an Amperian loop, write the equation, integration B dot dl is equals to mu naught into I. The problem that will be coming inside point, is any current? No, because all the currents are moving through this wire that is bent. So I consider the net current that is coming inside is nothing but 0. The net current that is coming inside is 0. That means the magnetic field at inside portion for a toroid is equals to 0. Very good result. Why we have to worry? Zeros are the best thing that can happen in physics, isn't it? Huh? Outside portion. Now what will happen that if I will tell you that for outside portion it also equals to 0? How I will be telling? See, this is a toroid. So if you are watching from this cross section, this is the way of current that is moving. What happened? See, this is the way how current is flowing. So I can say if the current is going, this is the inside going current and this is the outside coming current, inside going, outside coming. This is the way I think that you can imagine this in this way. Going inside, coming outside, going inside, coming outside. This kind of regular winding is going on. Okay. Now if that is the case, and for inside portion already I have told you that the net magnetic field is 0. For outside portion, how I will be calculating? Firstly, make an Amperian loop. Draw an Amperian loop. What is the equation you are going to write? B dot dl is equal to mu into I, net current flowing outside. If I'll ask you, tell me what is the net current. You remember for inside portion I have told you to write as minus, and for outside if current is coming you will be writing plus. So tell me, if this is minus current and this is same plus current, what is the net current? Plus I minus I. Tell me what is the net current? 0. So can you say magnetic field is again 0 for the outside portion? That means you will say, sir, there is no magnetic field due to a toroid. Actually, there is magnetic field, but it is not in the outside portion, not in the inside portion. It is in the mid portion that we will be having, and that is the actual case that we are going to understand. See, here what I am going to tell you. Now make an Amperian loop in between the loop. Make an Amperian loop, and now we will be getting the result. Let's suppose at radius r we are calculating. Write the result. B into line integral dl is equals to mu into net current. That means now this time if I'll ask you net current, only this portion will be integrated, inside portion. So I can say net current is going to be I only. So I will be writing here I only. Integration, and how many loops are also there? N number of loops are there. So we will be multiplying with the number of loops, that is I. Mu naught into number of loops is n into I. Into dl. What is dl vector? Integration of dl vector is going to give you 2 pi r because it is a circular. So B is equals to mu naught Ni divided by 2 pi r. This is the result that you are going to have for toroid. That is an important result. Please remember this for toroid. Simple result as compared to, if I'll ask you as compared to solenoid, it is very simple. Okay, because once you understand a solenoid from the core, toroid is the same thing. Toroid is nothing new. Okay. Fine. Now there is a basic question. Should we solve it? Easy question. Can you try it? Let's read the question firstly. What is the question saying? A toroid 1 and toroid 2. Two toroids are there. Have total number of turns 200 here. Total number of turns 200 and 100 turns for the second one. With the average radius of, this one is having average radius of 40 cm and the second one is having average radius of 20 cm respectively. If they carry the same current I, the ratio of the magnetic fields along the two loops. You have to tell me what is the ratio of the magnetic field due to the two loops. What is the result of toroid? B is equal to mu naught Ni divided by 2 pi r. Correct? Hence I can say magnetic field, if I am talking about the changing term, what are the things that are changing? Number of loops and the radius. So I can say, and rest of things are getting constant. So I can say B is directly proportional to number of loops, that is n divided by the radius, because the current that is flowing is same. So if I have to take the radius ratio of B1 by B2, exactly that is what you have to calculate, ratio of magnetic fields, correct? So what you will be writing? You will be writing N1 divided by R1, and here you will be writing R2 divided by N2. I hope that this much of basic things are clear to you. N1 is how much? 200. R1 is how much? 40 into R2 is how much? 20 divided by N1 is how much? 100. This will become 2, this will become 2, this 2 cancel, that means answer should be 1:1. 1:1, which of the option? Option D. Actually they are having the same magnetic field. After calculating the ratio, you are getting this result. Here what is the answer? 1:1 is the answer. Is it clear to everyone? Correct? So now we will be entering into the speed of a charged particle. Now how much force will be applied, how much speed will be there, acceleration will be there, what kind of path the charged particle will be following. These kind of things we are going to discuss in the next lecture. Until next time, keep learning, keep going with tapasya. Endigo and then digo namma tapasya.